this is joint work with Sebastiano Nicolussi Golo, who is in Italy, and with my advisor, Munduchin. And so first, where did this project start? The idea, it all came from a question that my advisor had about the Heisenberg group. And I'll define things later, but so first we can think of the Heisenberg group as points in three-dimensional space with a different group law. And there's a precise way to take those points in three-dimensional space and say, oh, these points are all vertical points and the rest are horizontal points. We can distinguish between those two directions. And then the question was, if we take a random walk starting at the origin, are you more likely to move in horizontal directions or vertical directions? And it seems like a very basic question, but there aren't any results that tell us, that give us an answer to that question yet. And so that's where the problem started, and that's why we started working on this project. And so, I've talked to some experts in random walks, and an expert in random walks would want to study the Poisson boundary. So study the I don't know very much about the Poisson boundary, but what I do know is that for the Heisenberg group and for all nilpotent groups, it is trivial. And so this boundary, which is normally related to random walks, doesn't give us any information about random walks in the Heisenberg group. It doesn't tell us anything about the directionality of a random walk. And so instead, so this is trivial, which is sad, and so instead we'll consider the horofunction boundary. And then the idea is that with this horofunction boundary, hopefully we'll be able to see more about the geometry and the directionality of random walks in the Heisenberg group. And this is a boundary that I'll define a little bit later, but it has some nice properties and it's very general. And so it can be defined for most metric spaces. All right. And so an example / experiment of what we were trying to do, but let's take a simpler case. Consider the group z squared and a simple random walk. So z squared can be generated by two elements, a and b, where we want them to commute. A simple random walk says if we start at the origin, we have a probability, and the probability that our next step is going to be A is the same as the probability that our next step will be B. Same for their inverses. And so at the origin, with equal probability, we'll step either up, down, left, or right. And then for the next step, we take the same probability, and we'll continue our random walk in that way. And so let's say this is the origin here. I guess I want to add a little bit more. So after one step, we know exactly what will happen. We can draw this sphere of radius 1, and we know with equal probability we'll be at one of these 4 vertices. And then if we draw the next sphere, we can run an experiment, or we can figure out with what probability we'll end up at one of these points, and we can get a probability measure on this sphere telling us the likelihood that the random walk will intersect this sphere at that point. And now, scale everything up. Let's suppose that this is the sphere of radius like 10,000 or 1,000,000 or however big you want it to be. We can experimentally run random walks until they intersect this sphere of radius 10,000, record that, and then from that get an idea of what a probability measure on this sphere would be. And the larger the sphere and the more random path, the more sample paths we take, a closer approximation we'll have. But we can see that we'll end up getting something on each edge. We'll get some sort of like Gaussian-like probability. Why? Because there are more paths that lead you here than that lead you straight north. And this will be the same on all 4 edges. And so we get this probability measure that's heavily weighted on the edges, on the centers of the edges specifically. And so where does the horofunction boundary come from? So I haven't told you what it is, and I haven't told you much about it, but it turns out that if you take a path that continues to go north or east forever, it never chooses north or east forever. It will always alternate between north and east in some way. All of those paths will converge to one point in the horofunction boundary. And then we have symmetry, so we'll also get points for northwest, southwest, and southeast. And then paths that eventually go north, depending on how they choose to go north, if they go directly north or if they go east and then north forever, they'll go to different horofunctions. And so we get a whole family worth of horofunctions corresponding to northward paths. We get a whole z, copy of z in between these. And symmetry tells us we get the same thing everywhere else. And so what does this experiment hint towards? What could we guess might happen is that if we want to get a probability measure on the horofunction boundary telling us which horofunctions we're most likely to converge to in a random walk, this would imply that we'll get a probability measure supported on these 4 vertices, each with probability 1/4, for this simple random walk. And so this is a little bit of a lie, because random walks in z² are recurrent, which means that with probability 1, a random walk will return to the origin infinitely many times. And so it's not escaping to infinity. And so all of this analysis is a little bit of a lie. But if we change this to to a d, and we let d be greater than or equal to 3, then the random walk is transient, and with a positive probability, it'll escape off to infinity, and then this analysis makes sense. But it's easier to draw in 2 dimensions than 3. And so we want to take this idea, this kind of like thought experiment, and translate it into the Heisenberg group, where the geometry will be a little bit more complicated. And so that's our goal, is to do something similar in the Heisenberg group and understand random walks and in which directions they're more likely to travel. All right. So now it's time to define some things. So first, what are we studying? The Heisenberg group. In the Heisenberg group, for a ring, like a commutative ring with identity, you can think of it as the set of upper triangular matrices such that x, y, and z are in our ring. For us, R is equal to, it's always going to be the real numbers, and we'll call it the real Heisenberg group, or the integers in the integer Heisenberg group. But I know people in, at least some algebraists at Tufts, like to study this for different rings other than this. I know that like mechanics sometimes study the Heisenberg group, and it's involved, the geometry of the Heisenberg group is sometimes involved in the study of optics. So the Heisenberg group comes up in a lot of different areas of math. And so it's a little bit surprising that there are seemingly simple questions that are still unanswered about it. So this is one representation of the Heisenberg group, but matrix multiplication is gross sometimes, and so we're going to define exponential coordinates for the Heisenberg group, and specifically I'm going to do it for the real Heisenberg group. So then HR is equal to R3, but we're going to put a different group multiplication on it. And what is the multiplication? It'll be additive in the first coordinate, additive in the second coordinate, additive, but then in the last coordinate we have a twist. And what's nice about these coordinates, well, x, y, z to the n is equal to nx, ny, and z for all integers n. So in particular, we know that the inverse of an element is just its negation. That's nice. So in the Heisenberg group, we also have a family of dilations for any positive t. We get a map we get a homomorphism of our group where the dilation by t of x, y, z is equal to tx, ty, t squared z. And the fact that this is squared is comes from the geometry of the Heisenberg group. And we'll see that a little bit later. And finally, what else do we have? We have a projection map, pi, which will go from the Heisenberg group to its abelianization. And in Heisenberg group, it's a step 2 nilpotent group. Its commutator group is just the subgroup generated by z, or this z. And so this is isomorphic to R2. So if we think of, it's kind of cheating, but we can think of this projection as if the Heisenberg group is all of R3 with this group law or group multiplication, then this projection is this projection down to the x and y coordinates. Cool. Any questions? Okay. So that's our group and our metric space, but we don't have a metric yet. And so now, time to talk about sub-Finsler metrics. And so, what is a sub-Finsler metric? So it's kind of like a Riemannian metric, but we change things. So Riemannian metric, to each tangent space, you associate an inner product. A Finsler metric, same thing, to each tangent space, instead of an inner product, we just want to associate a norm that may or may not be induced by an inner product. And sub-Finsler means that this norm is only defined on a vector subspace of our tangent space. So there are only some directions in which we can travel. Some directions are prohibited, and we will only calculate lengths of curves which travel in the correct directions. What?
Space. The space is of the same dimension in each point.
Yeah. Mm-hmm. Yes. And so why sub-Finsler metrics? So I guess one question I have for you is, are people familiar with Cayley graphs? Cayley graphs. for a group? No? Okay, so I'll define it. So before I tell you why we do this, I need to define Cayley graph of a group. So let G be a group. Generated by its generating set S. So I'm going to create a graph. What are the vertices? Vertices, the vertex set is equal to the set of elements in our group. And put an edge between G1 and G2 if and only if G2 inverse G1 is in our generating set. So if they differ by a generator, we put an edge. And so then we have our vertices and we have edges. We can say, okay, let's say each edge is length 1. That turns our group into a metric space. And this is an object that's used a lot in geometric group theory, where the goal is to take something algebraic, translate it into a geometric problem, see what you can understand, and see if that tells you something about the algebra of the group, or vice versa. So for example, the Cayley graph of Z2, where S is equal to 0, 1, 1, 0. I guess, yeah, we can just take that and we'll say that it's, we also want its inverses, but for the sake of making this graph, that gives us a grid. And that's the Cayley graph of Z2 for the standard generating set. Another example, let F2 be the free group. On two generators, call them A and B. Then the Cayley graph of F2 for those generators is equal to a tree. Where again, this is not drawn to scale. We assume that each edge has length 1. Yeah. So again, the question is, why do we care about sub-Finsler metrics? There's a theorem of Pansu from 83 that if we take the Cayley graph, so let G be a finitely generated nilpotent group for our case, let's just let it be the Heisenberg group. Then if we look at the Cayley graph of this Heisenberg group,
nilpotent group means that each element is nilpotent.
it means that its lower central series terminates Yeah, so G1 will be equal to G, or G0 will be equal to Z. G1 is equal to the commutator subgroup, and Gi is equal to Gi. Gi plus 1. Gi here. Yeah. And so for the Heisenberg group, one can show that the commutator subgroup is equal to the subgroup generated by Z. And this Z corresponds to 1, 1, 1, 0, 0, Z. And that commutes with everything else in that upper triangular group. And so that means that G2 is equal to like the trivial group. So we have a finitely generated nilpotent group, and so here, I didn't say it, but let this be the metric defined by this Cayley graph. It's the word metric defined by the generating set. So it's the metric on this graph. If we now scale that metric, or if we zoom out on the Cayley graph, this converges in the sense of Gromov-Hausdorff to the real Heisenberg group with a sub-Finsler metric, which we'll call the infinity metric. And so yeah, this is, if you haven't seen it, this is just a convergence of metric spaces. So the idea is, if we have this Cayley graph, we can think of it as like a mesh. As we zoom out, it becomes a finer and finer mesh until eventually it looks arbitrarily close to this Lie group with a specific metric. And this metric is sub-Finsler. And so recall that at the start, the goal was to study random walks in the integer Heisenberg group. It turns out that understanding the boundary of this group is a little bit easier because we have some more analytical tools we can use. But we want to study this group with this metric because this metric is closely related to the metric from the integer Heisenberg group, from this discrete group. Just like a fact that is that the integer Heisenberg group with this metric coming from its generating set from the Cayley graph, it embeds isometrically in this space that we will study. And you can embed it as a discrete lattice inside the Heisenberg group, the real Heisenberg group, isometrically. So What are some properties of this Sub Tensor metric? It's homogeneous with respect to dilations. In other words, the distance between the dilation of P and the dilation of Q for 2 points in our group is equal to the distance T times the distance between P and Q. It is left-invariant with left multiplication. And so I haven't really told you. So this isn't quite a property, but a question. What is this norm? So I told you that sub-Finsler metric comes from a norm. What you do is, so take your generating set S of the integer Heisenberg group. Consider the projection. And so now we have points laying in the plane. And take the convex hull of those points in the plane. So that'll give us a polygon. And from that polygon, we can associate a norm. That polygon will be the unit sphere. And that gives us a norm in the plane. And from that norm in the plane, we can define a metric on the Heisenberg group. So maybe it's time for an example. So Hz is generated by 1, 0, 0, 0, 1, 0, and inverses. Why? Because the commutator of these two, we'll call this A, and this B. We know that the commutator of A and B is equal to C, which is equal to 0, 0, 1. So those 4 points generate our group. So pi of S is equal to 1, 0, plus and minus 1, 0, and 0 plus and minus 1. And so the norm we get is the L1 norm. I think I want this to be up. Yeah. And so then I'll get another piece of chalk. And so this is the norm at the tangent space at the identity, on the horizontal subspace of the tangent space of the identity. So at E, we only consider paths passing through horizontally So we have this norm in R2, which is in the horizontal subspace. We can then take this norm in this plane and using left multiplication in our group, translate that plane and translate the norm throughout the whole group. And so we get a horizontal, a plane field via left multiplication we'll call it M, and MP is equal to xy 1/2 p1 y minus p2x. And so if we're at the point P in our space, the tangent space on which the norm is defined is given by all vectors of this form. Then the path gamma is called admissible if for all t the tangent vector at t is in this plane field. Without that. A fact that I won't exactly prove is that any 2 points in the Heisenberg group can be connected by an admissible path. And like, what's some justification for why that's true? The balayage lemma. So here we're going to utilize this projection. So if we have a path in the Heisenberg group, a path in R3, we can project it down to the horizontal and look at the path there in the plane. So if gamma is a path in R2, let's say starting at the origin, given, if you choose the path's initial height, because this is the projection, so given an initial height, there is a unique lift of gamma to an admissible path gamma, which is in R3. And the height, i.e. z coordinate of this path is given by the signed area enclosed Sorry. Break it. All right, let's try that. So we start off with a path in the plane, and we choose, and we're saying it's starting at the origin, we choose an initial height, then I can tell you exactly what the admissible path is. And this comes down to this here and a use of Green's theorem. And it gives us a unique path, a unique admissible path. So for example, let's say we have a path that goes like this. So this is gamma. Then if this is gamma t, and this is area, this has area A, then the lift of gamma t is equal to what we started with and A. And by signed area, if it's counterclockwise, it's positive. If it's clockwise, it's negative. And if you have a path that does something like this, that's plus area 1, that's minus area 2. Take the difference, and that's our z-coordinate for the lift of the admissible path that projects to this. And so that tells us that we are path connected in the whole group. And then what is the metric? The metric is take the infimum of all paths that connect P to Q and take the infimum of their lengths, and that's the distance between 2 points. And then what are geodesics? How do we find the shortest path between 2 points? Example, let's find the geodesic between 0, 0, 0 and 0, 0, 1 for the sub-Finsler metric induced by the L1 norm. And so what are all possible paths? So if we want to go from 0, 0, 0 to 0, 0, 1, we need a path in the plane that goes from 0, 0 to 0, 0, so a closed path that encloses area 1. So I could do that with a circle, and let's say this is area equal 1, that's a path. But it might not be the shortest. And so now we're fixing the perimeter, or we're fixing the area enclosed, and we want to know the shortest possible perimeter. So this is the isoperimetric problem for the L1 metric in the plane. And it's a fact that the isoperimetrics, i.e. the shape that encloses the most area with the smallest amount of perimeter for L1, which is this diamond norm, is a square. It's the dual polygon. And so that tells us that the geodesic between 0, 0, 0 and 0, 0, 1 is not this, but rather a square of area 1 traveling from 0, 0, 0 to 0, 0, 1. And so this has length 1, 1. And so then we have area 1. Thus, the distance between 0, 0, 0 and 0, 0, 1 is 4. So that's the shortest possible path. But this geodesic is not unique. I could draw another square like this that also has area 1 that connects 0, 0, 0 to 0, 0, 1, or its lift does. And so geodesics in the Heisenberg group with these metrics are not necessarily unique. Sometimes they are, but sometimes they're not. All right. And so I don't know if I'll get exactly where I wanted to, but let me just briefly tell you about the horofunction boundary. So okay, yeah. The horofunction boundary, nice property, yeah, or definition. So we'll embed our metric space xd, or x, into the space of continuous functions on x, just using the metric. So a point x will be sent to the function which measures the distance between x and the input variable minus this constant. So you have to trust me that this is an embedding, and then so for each point in our metric space, we have a function, and then we can take the closure in this function space. And so then the horofunction boundary is, we'll take an embedding, take the closure, and then subtract away what we already had. What's nice about this boundary, in a lot of geometric group theory, people look at hyperbolic spaces or spaces with non-positive curvature. And there are a lot of boundaries defined for those types of spaces. Those boundaries don't work well here. Because the Heisenberg group is not non-positively curved. It has mixed curvature. This boundary is still well defined. It's Hausdorff. And also any isometry of your metric space will extend to a homeomorphism of the boundary, which is useful when we want to look at random walks and how actions of the group on the space affects the boundary. And what can I say in like 2 minutes? So our model for studying the horofunction boundary of this space assume that Qn is a sequence that leaves all bounded sets, that goes off to infinity. If we look at the embedding, so if we want to look at, so phi of Qn is equal to the distance between Qn and let's call our input variable x minus the distance between Qn and we'll choose our base point to be the identity. Well, we can use first the homogeneity. So there's a unique constant such that the dilation by epsilon n of Qn is in the unit sphere of this metric. And so this function is equal to, we'll call this Pn, and it lives on the unit sphere. And this is equal to Pn and the dilation by epsilon of n of x minus the distance between Pn and E. Then we can use left invariance of the metric to say that this is equal to the distance between the identity and Pn inverse minus the distance between Pn and E. Oh, this should be divided by epsilon of n, and this is divided by epsilon n. Or let's do E and Pn inverse. And so if we think of it as like, so we're measuring the distance between identity and Pn inverse and then pushing slightly off it, because epsilon of n is going to 0. If Q of n is going to infinity, then we have to dilate by smaller and smaller things to bring it back to the unit sphere. And so we're looking at the sensitivity of, if f of x is equal to the distance between E and x, we're looking at the sensitivity of this function near p sub n inverse. And so this is, it looks kind of like a derivative, and it is a derivative called the Pansu derivative. And so we study the horofunction boundary by doing some analysis with these derivatives on the unit sphere of the Sub Tensor Metric. And so we understand what the horofunction boundary is for this. Our goal now is to restrict to the case that we're in the integer Heisenberg group. What sequences are allowed and what functions do we get? And then from that, the next step is to see what we can say about random walks from that. But yeah, I'll stop here.